The word free in the phrase free thermal strain again means that when we apply a temperature change and the material or the solid is unrestrained, then it's free to grow. I'll say free to move. And that's important because we're going to look at a lot of problems where there may not be restraint. So it means that if we take a cookie sheet in the oven, so an example of this would be a cookie sheet in the oven, and we apply some temperature change, then it expands. And that's our free thermal strain. So that is our alpha delta T. But the important thing is if we cut a free body diagram and look at the edges and look at the forces on it, other than the force that's generated by its own gravitational support, then if we make a cut and draw a free body diagram, there is no stress. So it's possible to have strain without stress. This is our one example, our first example of that, I should say. It's not the only one. So we can have strain without stress. It's a little bit of a different animal than what we've been referring to. So to distinguish between those two effects, we frequently will break the strain down. And we'll do that by referring to total strain. So we will introduce, and we'll write this as an ad hoc designation. So we'll call this the total strain. And we're going to use a phrasing that I think is extremely useful for us to introduce. We'll call this what we see and measure. In other words, if we go into an experimental system and we have a change in length over length or a change in angle, then that is what we're referring to as the total strain. And we break that total strain down then into two parts. So we'll write it like this. We'll write it as epsilon sigma plus epsilon thermal. Now this is frequently called mechanical strain. And remember on day one, when we introduced the meaning of the word mechanics, mechanics means response to force. So there is a force that's causing a stress that causes a strain, and that's referred to as mechanical strain. This is the one that we just measured. This is our free thermal strain, but we'll also just abbreviate it as being the thermal strain, which is equal to the alpha delta T. So the total strain, what we see and measure, is broken up into mechanical strain and the thermal strain. And so how does that manifest itself for, say, an axial bar? Well, the total strain then, in that case, is going to be equal to the mechanical strain. Well, that's sigma over E. That's our one-dimensional constitutive law, plus an alpha times delta T. So there we have a constitutive law, and what we do is we modify then the strain stress law, and we put that thermal strain over here. So alpha goes on the right-hand side when we're writing out our constitutive relation. So typically we have seen that I'll put three little dots. Therefore, this means that the alpha part goes into the constitutive law, or the stress strain, when we write out our expression for strain. So when we write epsilon total is equal to whatever. So we have the mechanical strain, that is the strains caused by the stress or stresses, and then we just plop on the alpha delta T term that we have. Now it's also important to note when we do our thermal effects that there is no such thing for our isotropic materials as a thermally induced shear strain. So there is no gamma thermal for an isotropic material. That means that if we have a rectangular section, and we've got our original right angles, and we have a delta T, then it's going to grow. Again, if for most materials it's going to grow like this, but it stays at 90 degrees. So there is no shear strain or shear thermal strain, and there's no Poisson effect. So there's no Poisson thermal. That means that if I have a material like this, and we apply a delta T, then this strain is going to be an alpha delta T, and this strain is going to be an alpha delta T. In other words, we don't apply a Poisson ratio on that strain to say it's in the transverse direction. So there is no mention of the Poisson ratio when we do this. So the thermal strain in all directions for an isotropic material is the same. So the epsilon thermal is the same in all directions. All right, so now we've got a little bit better idea about how thermal strain is going to be introduced. Now, let's go ahead and introduce an example problem that I think not only is it a classic, beautiful problem, but it'll help us figure out what we mean when we're saying, what we see and measure, and what the difference is between the total strain and the thermal strain and so on. So this is a terrific example. Again, all the examples that we do are great, but this is even greater still. This is a great example. Mainly because it has a lot in it, even though it's relatively simple. You've probably seen behavior like this in your past experience, and it'll give us a little bit of practice in terms of what we're going to be trying to do. So what we're going to do is we're going to take a rigid foundation, like so, and like so. So that is rigid, and remember, that means it cannot move, it cannot deform. And we are going to put a steel bar that exactly fits. It is a snug fit that is 20 feet long, like so. So that is a steel bar. And here are its properties. The steel bar, first off, it has a modulus elasticity of 30,000 KSI. That is a very common number for the elastic modulus of steel. It has an alpha. Now notice the size of this. This is 6.5 times 10 to the minus 6th per degree Fahrenheit. So remember, it's inches per inch upstairs, or length per length. It could be inches per inch, meters per meter, millimeters per millimeter. It doesn't matter. That is a dimensionless quantity. But that's how much strain there is per degree change in temperature. And its area is going to be 12 square inches. So those are the parameters of our particular bar. So we place it inside. It is a perfect fit. And it is smooth at the ends. And we say it's smooth at the ends because we don't want anybody to be worried that it's going to catch and not be allowable to be expanded at the end and so on. So it is nice and smooth, and so there's nothing else that's going to be generated as we do this analysis. All right, well, the forcing function is we change the temperature, 80 degrees. And if you've lived in Colorado long enough, you know that that's possible. It may be, that'd be a wild day, but it's certainly something that might be at least within the realm of possibility. And we want to know then, what is the force that's generated on the rigid foundation? Question mark. All right, so if we just think about this without doing any analysis, we just give it a little bit of thought, then as the steel is heated, it wants to expand. So notice, the steel wants to grow, but we don't let it. And the fact that we are not letting it expand means that there's going to be some sort of stress generated inside of that. And then if there's a stress, then we're going to have an axial force. Well, now we can use the constitutive law that we introduced just a couple minutes ago, and that is the total strain, what we see and measure, is equal to the stress divided by the modulus elasticity plus the alpha times delta t. There it is. Total strain, which is what we see and measure, is the stress divided by the modulus elasticity plus coefficient of thermal expansion times the change in the temperature. Now, here's the crucial part. If we look at the total strain, there is a perfect fit before it deformed. The bar was 20 feet long. Then we apply temperature change. It wants to move, but it can't. Therefore, the total strain, what we see and measure, is 0. That's a key fact. So that it does not expand. And this isn't a trick problem, but that is a crucial issue. And so that is a very, very key observation, that it wants to grow, but it can't. Therefore, the total strain is 0. And that's going to then be equal to sigma divided by E plus alpha times delta T. And that also is just on time to have us end part C of this lecture.